Using the idea of entropy that we've already come up with and the equation that we just derived, we can now do an example. So let's consider two blocks in thermal contact, a hot block and a cold block. The initial temperatures of each of the blocks are 400 Kelvin and 300 Kelvin, and they're both made out of aluminum. What is the change in entropy of each block of the system and the system as a whole when it comes to equilibrium? So let's gather information. First thing we need to do is draw a picture. So we have our two blocks. This is the initial conditions where the cold block is at 300 Kelvin and the hot block's at 400 Kelvin. And we know that each block is made of aluminum, so we can write the heat capacity down for both blocks, which is 90 joule per Kelvin. And we can use the equation that we just derived, and we can see that we have the heat capacity C. For each block, we can measure this change in entropy using its own C, its own initial temperature, but we need the final temperature. And luckily, this final temperature will be the same final temperature for both of the blocks. Let's organize our approach. We need to find this T final, and we know that we can define the change in heat as the heat capacity times the change in temperature for each of the blocks individually. We also know that the total heat transfer for the whole system is equal to 0 because there's no heat coming in or out. So all of the heat that's transferred from the red block goes into the blue block. Now, if you just looked at this simple equation, you would think that the total entropy for the whole system is equal to 0 because change in S is equal to change in Q over T. The problem is that it's not quite as simple as that. So that's why we need to do out the whole question and actually find TF. And if it was the case that the delta S was 0, then this would be a reversible process in the sense that it would spontaneously go back to the initial condition. But we know for a fact that the hot block and the cold block will come to an equilibrium with a temperature in between, and that they will not spontaneously return to 300 and 400 Kelvin separately. So let's analyze this. So we have our equations. We know that the sum of the delta Q's have to equal 0. That means that the loss of heat from the red block has to equal the gain of heat from the cold block. So we can look at the hot block and plug in for this equation, and we can see we get this equation, C times TEQ minus 400 Kelvin. Same thing for the cold block. And we can use the third equation to set them equal to each other, equal and negative to each other, or sum of the delta Q's is equal to 0 for this system because it's an isolated system. And so we can see that the C's will cancel off of both of these, and we can rearrange. We get 2 TEQ is equal to 700 Kelvin, divide by 2, and TEQ is 350. Now this is dead center right in the middle of the two initial temperatures. You could have probably guessed this, but it only works if the C's are the same, if they're made out of the same material. If the two different blocks were made out of different materials, it wouldn't be dead in the middle. One of them would be able to give more heat than faster than the other one could accept. So now we can use this information of T final and plug into our entropy equation. So we can see that the hot block is going to lose entropy, and it's going to lose negative 12 joules per Kelvin. But the cold block is going to gain entropy, and it's actually going to gain more entropy, 13.9 joules per Kelvin. So now we've done one part of the system, which is finding the change in entropy for each block separately. And to find the change in entropy for the system as a whole, we just add these together. We get 1.9 joules per Kelvin. Now we can see very clearly that delta S is greater than 0, and this is not a spontaneously reversible process. That these blocks will come to equilibrium and they won't return to their initial temperatures without a lot of effort on our part.